This video discusses quantifiers, including negating quantifiers and combining them. We'll be dealing with two basic quantifiers. The first is the existential quantifier. It means that something exists. The notation that we use looks like a capital E backwards. Think E for existence. And the other is the universal quantifier. That means for all, for every, for each, some property is universal. And the notation for that looks like a capital A upside down. So E for existence, A for all. Let's look at how we might use these. Here's something we already know the definition of. A divides B. So A divides B, according to what we've done before, means that there is some integer C, or let's call it K. There is some integer K so that B is equal to A times K. So the only thing new here is that we're going to introduce notation for this. There is some integer K. So we could read this directly and say there exists K is an element of the integers so that B equals Ka. But we're going to translate that more smoothly. There is some integer so that B equals Ka. And the so that is often left out of that phrase. But the so that goes with the existence quantifier. I would very seldom just say there is an integer. What I care about is that there are certain properties that go with that integer. So the so that is with the existence quantifier. We've seen a universal quantifier. In this example, A is a subset of B. What that means to us is that every element of A is an element of B. So that's saying something about every element of A. That's universal. Our new notation for that looks like this. If I were to read this directly, it would say for all A, an element of the set A, an element of the set B. But again, we don't do a direct translation of the symbols. We read this more smoothly to say for every element of A, that element is an element of B. So how do we prove statements like this? Existential statements are usually quick to prove if they are true. To prove that there exists an X so that assertions about X, whatever they may be, are true, we simply have to show one. So that's quick, but not always easy. On the other hand, to prove a universal quantifier, to prove a universal statement, if we want to prove that for every element in A, certain assertions are true, we can't just pick one. We can't even show several examples. We need to show that it's true no matter which element we choose. So here we'll consider an arbitrary element. I often call this a generic element. We don't get to choose which one. All we get to say is that it is in A. And then we need to show that it satisfies these assertions, whatever they may be. Let's look at some examples. If I want to prove that there is an integer x so that x squared equals 4, all I have to do is exhibit one. So here's my proof. 2 squared is equal to 4. That's enough. Let's try this one. I want to prove that for every integer x, the quantity x times x plus 1 is even. So pause a minute and think about whether you actually believe that this is true, and then think about why you believe it. And you will probably end up thinking about two different cases. We know that one of these two numbers, either x or x plus 1, is going to be even. That's not an obvious thing, but we know it's going to be true. We've got a lot of experience with integers. So here's how I'll attack that. First, let x be a generic integer, an arbitrary integer. I don't get to pick which one. If it's even, then that means that there exists an integer k, so that x is equal to 2k. Well, now let's look at x times x plus 1. X is equal to 2k. And honestly, I don't even care what x plus 1 is here. We know it's 2k plus 1, but I don't even need to know that to know that this entire expression is even. And that's what we wanted. Okay, so we know what to do if x is even, we're done. But maybe x is not even. The other case is that x is odd. So here's what we did when x was even. If x is odd, then what do I know? Well, I know that there is some k. Notice this is a different case, so it's okay if I reuse the name k. We're not dealing with x is even, we're only thinking about the case where x is odd. There is a k, so that x is 2k plus 1. Right? And that means that x times x plus 1 is 2k plus 1. And now I do care about the form of x plus 1. It's 2k plus 1 plus 1. Notice I wrote this a little oddly because I substituted 2k plus 1 directly in for x. So let's look at what this is. This 2k plus 1, I don't want to multiply out until I simplify this second factor and call it 2k plus 2. So I don't need to multiply these together. Instead, I'm going to notice that I can factor out a 2 from this second term. So that's what we'll do. This is 2k plus 1 times 2 times k plus 1, which I can tell is even because of the factor 2. We've dealt with the case where x is even, we've dealt with the case where x is odd, and those are the only two possibilities, so it must be that indeed, for all integers x, the value x times x plus 1 is even. Now, what happens when we start putting quantifiers together? This sentence says that there is an integer x, so that for every integer y, x times y equals 0. Notice, in order to prove an existential quantifier, an existential statement, I would have to exhibit such an x. So can we prove that there is some integer x so that no matter which y you choose, x times y will be equal to 0? Well, we can because of 0. We'll let x equal 0. How about this one? This reads, for every integer x, or I could say for any integer x, there is an integer y, so that the following condition is true. X plus y is equal to 0. So this is saying if you give me any integer at all, x, I will be able to find some y so that x plus y is 0. I claim that this is true. So if you were to give me x equals 2, I would choose y equals negative 2. How about this one? There is an integer x, so that for every integer y, x plus y is equal to 0. How is this different from the last one? Well, notice that the order is different. Here we've said there is an x so that for every y something is true. So if you wanted to prove that this is true, you'd have to be able to exhibit some x. Show me an x that works. What does that mean? If you give me y, well, you don't give me y. I have to choose x first, and it has to work for every possible y. And that can't happen, right? We can't find a single x that works for all possible y. So this is a false statement. How about this? For every integer x and every integer y, x equals y. That really says all integers are equal, which we know is false. For every integer x, there is some integer y, so that xy equals 1. Looks promising. If I were given x, I could find y as 1 over x. But y is supposed to be an integer, and the problem is that this is not always, but not usually an integer. So this is a false statement. Every integer has an integer reciprocal. That's false. How about this? There is an integer x, so that for every integer y, x is greater than y. Let's think about what that's really saying. There is an integer x, so that for every integer y, x is greater than y. There is an integer x which is larger than all other integers. Well, not even all other integers. This doesn't say that x and y have to be different. So there is some integer which is larger than all integers. And we know that that's not true. There's no maximum integer. If we want to negate a statement, think of negation just like you would in the English language. The notation we're using for this is this square bracket. Not, right? Some of you may be used to using the tilde, and that's just fine. If you're used to using that, feel free to use it. Either one of these is a valid notation. So not A means that the statement A is not true. So A is false. It's the opposite truth value from A. So not x greater than 0 means x is not greater than 0. In other words, x is less than or equal to 0. If the statement in parentheses here is negated, the statement in parentheses says there is an x in set A so that certain things about x are true. If it is not true that there exists an x with certain properties, there is no x with certain properties, and that means all of the x's do not have those properties. So when we negate an existential quantifier, we get a universal quantifier. And notice that that negation sort of pushes through to the next statement. So for instance, the statement in parentheses here says there is an integer, x, so that x squared is less than 0. We know that's not true. There's no integer with a negative square. So the negation written here must be a true statement. Negating the existential quantifier. We're just going to write this in a simplified form. Get rid of that negation statement. It says for every integer x, it is not true that x squared is less than 0. We keep simplifying. For every integer x, x squared is greater than or equal to 0. Suppose we want to negate a universal statement. The universal statement here is that for every x in A, certain assertions about x are true. So if something is not true for every x, that means there's some x for which it is not true. So the negation of a universal gives us an existential. The statement in parentheses here says for every integer x, x squared is greater than 1. We know that's not true because there exists an integer x, so that it is not true that x squared is greater than 1. That is, there exists an integer x, so that x squared is less than or equal to 1. Here's my proof. 0 squared is less than 1. 1 squared is less than or equal to 1. Negative 1 squared is less than or equal to 1. So really, any of those three would consist of a proof of this statement. Here we're negating a combination of quantifiers. You can think about what's being said here, or you can just do it algebraically. Notice that that negation pushes through to the next phrase each time. The original statement in parentheses said, for every x and y, x is equal to y. We know that's not true. There exists a pair x and y where x and y are not equal. If we negate this statement, negating the universal gives us an existential. Negating the existential gives us universal. Negating equality gives us inequality. Here, negating existential gives us universal. Negating the universal gives us existential. And negating a strict inequality gives us a non-strict inequality.